This question is about a light bulb filament, but we want to look at the electric field. We want to look at the motion of charges inside the light bulb filament. And for starters, what we want to do is just sketch a picture. Okay, so we imagine we've got a light bulb filament. Okay, and between the two ends of the filament, we put a potential difference of 120 volts. Okay, the length of the filament is 60 centimeters or 0.60 meters. That's our length. And then we put a potential difference across it. And so inside the filament, there's an electric field. The electric field points from high potential to low potential. And this electric field causes the motion of charges. And if we have a stronger electric field, it's not a surprise to say that we're going to have charges moving. We'll have more charges in motion. And so we're going to have a higher current. Now, with that in mind, with this picture in mind, let's just cut to the chase and think about our solutions. Okay, so we're going to do some solving. First off, the question asks this: if the potential difference is 120 volts, what's the strength of the electric field inside the filament? Well, the electric field is just delta V over D, and we know those two values. The difference in potential between the two different sides is 120 volts. The distance between the two sides is 0.60 meters. And so we just calculate an electric field of 200 volts per meter. Now, if we double the length of the filament without changing the diameter or the potential difference across it, what's the new electric field? Well, the new electric field is just, again, delta V over D, except let's let it be primed here. So the new electric field is the same potential divided by the new distance. Well, the new distance is not 0.60 meters, it's double that. It's 1.20 meters. And so I end up with an electric field of 100 volts per meter. And that makes sense. I have twice the distance, and so I expect half the electric field. That's exactly what we'd expect. Okay? Next up, if the current in the filament is proportional to the electric field, what is the current in the filament following the doubling of its length? Well, first, let's calculate what the filament current is originally. Okay, originally we calculate the current this way. The power in the filament is equal to the difference in potential times the current. Well, the power is 60 watts. So the current is equal to the power divided by the potential difference, 60 watts divided by my potential difference, and the potential difference is 120 volts. And so the original current is 0.50 amps. That's my original current. What's the new current? Okay, with the new current, it's just going to be half that. The current is proportional to the electric field. We're told that. So therefore, the new current, after we double the length, is just equal to 1/2 of 0.50 amps, or 0.25 amps, half the current. And that makes sense. We're not pushing as hard, and so we don't expect to have as much motion of charges. So we should have a smaller current. Finally, we're going to take a look at this. What is the resistance of the filament following this doubling of the length? Well, we can calculate the resistance just using Ohm's law. Okay, Ohm's law is this. I is equal to delta V divided by R. We can rewrite it this way. The resistance of the filament is just equal to delta V divided by I. Well, delta V divided by I is equal to 120 volts, or let's put a prime here. So the new resistance is equal to the same potential divided by the new current, 120 volts divided by the new current of 0.25 amps, and so I end up with 480 ohms. That's what I get for the new resistance. Now, one of the reasons for doing this problem is so that we can look at the relationship of these different variables. Look what's happened. I've doubled the length, so I've halved the electric field. I have the electric field, and so I have the current. I've halved the current, and so I've doubled the resistance. And our assessment is really straightforward. We'll say, look, we were told that the resistance of a filament, or of any wire, or of any conductor, is just resistivity times length divided by the area. I haven't changed the resistivity because it's the same material. I haven't changed the cross-section area. We're told that, but I've doubled the length. So the resistance is just proportional to the length. If I double the length, I expect to double the resistance. And it started with a resistance of 240 ohms finishes with a resistance of 480 ohms. And so, in fact, our final result matches our expectations of how the world works.